Okay, so let's talk about the existence of derivatives. So a function f is differentiable at a if f prime of a exists. Otherwise, the derivative doesn't exist. So there are a few cases when the derivative won't exist. So remember that the derivative means slope. When does a function have a slope that doesn't exist? And it's when the slope is vertical. So a function that is increasing until a vertical moment right here, that tangent that we draw, there'll be a vertical tangent. We're saying this is point A. And so this has an undefined slope. S-L-O-P-E. And so the derivative won't exist because there is a vertical tangent at x equals a. Okay, the derivative won't exist also if the function doesn't exist. So a function cannot exist because of discontinuities. For example, a VA. Right, so if this is the value A1, and the graph then goes like this. All right, the derivative at A1 won't exist because there is no function. Another time we can have no function is when we have a hole. So there's a hole at A2. Another time is if the function has a jump. And so at 3, the function exists, except it jumps, and then there is no derivative here either, because we can't describe the behavior around a jump. So there are discontinuities that can cause the derivative not to exist. For example, a VA, like at A1, a hole, like at A2, and a jump at A3. Okay, another time a derivative doesn't exist is if there's a corner. For example, an absolute value function. So this is x, but shifted to the left by some value of a. So this is a corner. So anytime you've got like a sharp turn, because the derivative on the left is -1 and the derivative on the right is +1. And so those derivatives, like, there's no smooth transition between those two abrupt numbers. Also, another time you can have a vertical tangent is with a cusp. So a cusp is like, looks like a seagull. Well, because I'm not an artist. And this is like, this is the absolute value of the root of x. So then you can get like negatives over there. This is called a cusp. Okay, because also if you were to draw the tangent at that cusp part, right, my slope would end up being vertical. Okay, so let's do a couple algebraic proofs to show whether something is or is not differentiable at a certain value. So is the cube root of x differentiable at x equals 0? So we don't know what this graph looks like. We know what the root of x looks like. We haven't looked at the cube root of x. So let's just try it. So like f prime of x will be the limit as h approaches 0 of the cube root of x plus h minus the cube root of x all over h. Direct substitution won't work. The cube root. Okay, and then also we're like in trouble here because we don't know how to deal with cube roots like this. We can't use a conjugate binomial. Also, U substitution is not going to work because the cube root of x and the cube root of x plus h are like completely different terms. We'd have to sub in two values. But luckily, we're being asked about the derivative at a certain value. We don't actually have to find the general derivative of this. We are trying to find the derivative actually right away at 0. So plugging in 0 for x just gives us the cube root of h divided by h. Okay, now this thing is actually like there are powers with the common base, right? So we can divide h to the power of a third by h, which would make 1 over h to the 2/3. Okay, and now this limit doesn't exist. It's in the simplest form possible. And if I put h towards 0, I am getting a 1 divided by 0 value. Like if I substitute in h equals 0, I'm getting undefined value. So this limit doesn't exist. So then f prime at 0 does not exist. Okay, or f at x is not differentiable at x equals 0. Okay, maybe pop it into Desmos and see what that graph looks like and which of these 4 cases it visually is. Okay, next let's show, so we showed that like the absolute value function will have a corner. Let's talk about why it's not differentiable at that corner. So find the derivative using first principles. So the root of x plus, the absolute value of x plus h minus the absolute value of x over h. Okay, we have 0 skills for being able to clear up absolute value signs. So let's just right away plug in the 0 for x, and you'll get the the absolute value of h over h. Okay, so now we're trying to find a limit of this function. We don't know how to find the limit of this function, so a strategy that we have is we can do left side, right side limit and see if this limit exists. So let's even ask this question. Does this limit exist? Okay, you can see pages 6 and 7 as a refresher of this. But what we're going to do is find the limit as we approach from the left and the limit as we approach from the right. Okay, so on the absolute value function, if we call this the absolute value of h, then our negative h's inputs are on the left, our positive h inputs are on the right. And as we are moving from the left, right, the slope of this is, the value of it, of the absolute value of h is the value that's the negative of h. And so this gives us a limit of negative h over h, which is -1. And the limit of a constant from our properties is just the value of that constant. Right? And what we even know is the slope of the line on the left of an untransformed absolute value is just -1. So over here on the right side, the input of h gives you an output of h. And then h divided by h is 1. And the limit of 1 is 1. So then we can see that the limit from the left does not equal the limit from the right. Okay, so this limit doesn't, as we approach 0, doesn't exist. Therefore, we cannot find the derivative at x equals 0. Okay, and so that's how we tell, that's how we're able to prove that a derivative doesn't exist at a certain value. All right, so that's Unit 1. We can talk in a lot more detail now about behaviors of graphs and the rate of change of graphs and the tangents of graphs.